Hi everybody. I think a lot of you are super close to being able to get this, so let's go a little more slowly and carefully through this same quadratic example of proving a limit from the epsilon-delta definition. So we're going to show that the limit of x squared as x approaches 2 is equal to 4. Remember, this limit stuff is not a way of finding limits that you couldn't find before. The goal is not to calculate something new. It really is a definition of what it means for a limit to exist. So I think your intuitive idea of what it means for this limit to exist is something like this. As x gets closer to 2, x squared gets closer to 4. So I want to show you that all of this epsilon delta stuff is really saying just that exact same thing. So there's the intuition. Put slightly differently, the same thing could be stated this way. I can get f of x as close as I want to 4 if I can get x close enough to 2. Put this way, it maps very cleanly onto this formal definition. So let's look at what some of the pieces mean. So this absolute value, x minus 2, this is just a way of describing what is x's distance from 2. And this absolute value, x squared minus 4, is describing what is x squared's distance from 4, or what is f of x's distance from 4. So if I'm saying I can get f of x as close as I want to 4, a different way of saying that is that this distance of f of x from 4 can be as small as I want it to be. I can get this distance as close to 0 as I want. So put that way, this epsilon is a number that says how close do I want f of x to get to 4. Put differently, how small should this distance of f of x from 4 actually get? And by setting this epsilon to be smaller and smaller, we're saying that we can get this distance as close to 0 as we want it to be. So if I'm saying that I can get f of x as close to 4 as I want, if I can get x close enough to 2, the question would be, well, how close does x have to get to 2 in order to make it happen? And that's what delta measures. So delta is some number where if someone says, I want to get within 1/10, I want f of x to be within 1/10 of the limit, we're going to say, okay, here's a number, and as long as x is within this distance of 2, I'm sure that we can get f of x within your distance of 4. The more you can really feel this definition in your bones, the more sense the proofs are actually going to make. Because if you don't understand the overall goal of what we're doing here, all of the algebra won't make any sense at all. So again, one more time, just remember how intuitive it feels. We're just trying to show that as x gets closer to 2, f of x gets closer to 4, and we're doing that in the following way. We're saying you can get f of x as close as you want to 4 if you can get x close enough to 2. And the way that we're going to show that is by responding to a challenge. If someone gives us epsilon, which is some number which tells us how close do we want to get to 4, we can always find a number delta that will tell us that's how close x needs to be to 2 in order to meet the challenge of making f of x that close to 4. Okay, let's take one quick look at this in a graph, because I think that's going to make it make a lot more sense. So here's a graph of x squared, and you can see that when x is 2, it looks like x squared is 4 here. And so what we're trying to say is that as x values get closer to 2, y values get closer to 4. But the way we're doing that is using this epsilon delta definition. So in this case, epsilon is 1. So you can see that we've got this huge range here. This is called the epsilon neighborhood around the limit. So when when y values are between 3 and 5, they're in this epsilon neighborhood because they're within a distance of 1 of the limit we're trying to get to. So the claim was that no matter what epsilon you find, you can always find a number delta so that as long as the x values are within that distance of 2, all those x values are going to map inside this epsilon neighborhood. Well, clearly in this case it wasn't very hard to find one. Although if you make the delta number big enough, well, we've turned red here because now some of the x values within a delta distance of 2 are not mapping inside the epsilon neighborhood. So if you know what your epsilon is, like let's make our epsilon 1/2, whoops. So if you know what your epsilon is, you can use your calculator or you can use a graph, and it's really easy to find a delta so that all the x values in the delta neighborhood of 2 are going to map into the epsilon neighborhood of 4. The tricky thing is we have to come up with some way of guaranteeing that no matter how small this epsilon window gets, you can always find a delta neighborhood so that all the x values will map into the epsilon neighborhood. Well, clearly there's some kind of relationship here between epsilon and delta. I know that as my epsilon gets smaller, my delta is also going to have to get smaller. So if we could describe that relationship with an equation, if we could say what is delta in terms of epsilon, that might be a good way to guarantee that we can always find a delta that will work. So here's an example. What happens if we say delta, what if this delta window always has to be half the size of the epsilon window? That makes sense because then the delta window is always smaller than the epsilon window because I know it's half the size. So let's give that a try. Here's delta. I'm going to make it equal to epsilon divided by 2. Okay, well, sort of looking visually, it looks like, take this length, and it looks like my delta window is half that length. But very clearly, as I move my epsilon around, my delta window is too big. So I know my delta window needs to be even smaller than epsilon over 2. Oh yeah, this is never going to work. Okay, so what if we make our delta equal to epsilon over 3? So our delta window is a third the size of the epsilon window. Well, that's not working. 4, 5, aha. So it seems like, again, we're not proving anything, we're just experimenting. But it looks like if my if my delta window is 1/5 the size of my epsilon window, that delta value is always going to work. It looks like it. We don't know yet, but it looks like it. Okay, so enough experimenting. Let's actually figure out how we can establish what is this relationship between epsilon and delta.